For devices that transfer large quantities of data, it is wasteful to tie up the CPU transferring data in and out of registers 1 byte at a time. Instead, this work can be offloaded to a special processor, known as the Direct Memory Access or DMA controller. The host issues a command to the DMA controller, indicating the location where the data is located, the location where the data is to be transferred to, and the number of bytes of data to transfer. The DMA controller handles the data transfer, and then interrupts the CPU when the transfer is complete. A simple DMA controller is a standard component in modern PCs, and many bus mastering I/O cards contain their own DMA hardware. Handshaking between DMA controllers and their devices is accomplished through 2 wires called the DMA request and DMA acknowledge wires. While the DMA transfer is going on, the CPU does not have access to the PCI bus, but it does have access to its internal registers and primary and secondary caches. DMA can be done in terms of either physical addresses or virtual addresses that are mapped to physical addresses. The latter approach is known as direct virtual memory access, and allows direct data transfer from one memory-mapped device to another, without using the main memory chips. Direct DMA access by user processes can speed up operations but is generally forbidden by modern systems for security and protection reasons. User application access to a wide variety of different devices is accomplished through layering, and through encapsulating all of the device-specific code into device drivers, while application layers are presented with a common interface for all devices. Devices differ on many different dimensions, as outlined in this figure. Most devices can be characterized as either block I/O, character I/O, memory-mapped file access, or network sockets. A few devices are special, such as time-of-day clock, and the system timer. Most OSs also have an escape, or backdoor, which allows applications to send commands directly to device drivers if needed. In Unix, this is the IOCTL, or I/O control system call. IOCTL takes 3 arguments. The file descriptor for the device driver being accessed, an integer indicating the desired function to be performed, and an address used for communicating or transferring additional information. Block devices are accessed a block at a time and are indicated by A, B, as the first character in a long listing on Unix systems. Operations supported include read, write, and seek. Accessing blocks on a hard drive directly is called raw I/O, and can speed up certain operations by bypassing the buffering and locking normally conducted by the OS. A new alternative is direct I/O, which uses the normal filesystem access, but which disables buffering and locking operations. Memory-mapped file I/O can be layered on top of block device drivers. Rather than reading in the entire file, it is mapped to a range of memory addresses, and then paged into memory as needed, using the virtual memory system. Access to the file is then accomplished through normal memory accesses, rather than through read and write system calls. This approach is commonly used for executable program code. Character devices are accessed 1 byte at a time and are indicated by A, C, in Unix long listings. Supported operations include get and put, with more advanced functionality such as reading an entire line supported by higher-level library routines.